And we now have Vincent Sécherre, who will speak to us on self-dual cuspidal representations of GLM and distinction by an inner involution from Université Versailles.
Thank you. Thanks to the organizers for this invitation. So there is a slight difference with the title I gave you 1 or 2 months ago. So it will be more generally about inner forms of GLM, but I will explain that. So in this talk, I would like to illustrate how the explicit description of cuspidal representations of p-adic groups, as discussed in Vincent's talk, can help to investigate distinction problems. So I will be interested in this talk in a very specific example of a distinction problem. And so I'm going to explain what it is. And so first, let me fix some notation. So first, F is a non-Archimedean locally compact field of residue characteristic some prime number P. So for the moment, P and F are arbitrary, but soon F will have a characteristic 0. And as soon as well, P, I will assume P is different from 2. But for the moment, they are arbitrary. Next, let A be a simple central F-algebra of finite dimension over its center. So it is isomorphic to an algebra of matrices of size R with coefficients in some division F-algebra D with reduced degree denoted D. And I will assume that the product RD is even, denoted 2n. Then I fix, first, let G be the group of invertible elements in A. So it is isomorphic to GLRD, which is, by construction, an inner form of the split general linear group GL2NF. Now let K be a quadratic separable extension of F, and assume that it is contained in A as an F-algebra, and let H be the centralizer of K in the inner form G. We can describe K more precisely. Since K is quadratic separable, we can choose an element delta in the field, which generates K as an F-algebra, and assume that the square of delta is some element alpha, non-zero element alpha in F, and alpha is well-defined and characterizes K modulo the squares in F. So if we fix such a delta, then
sorry, Vincent.
Yes.
After F delta to the right, I cannot read anymore.
Okay. So I choose delta so that its square is an element, so denoted alpha in F. And then H can be described as the subgroup of G made of fixed point by the involution tau. So by definition, tau is conjugacy by delta, and tau is the inner involution of G, which appears in the title. Now, so I will be interested in representations of G, which are distinguished by H. So what does it mean? An irreducible. So all representations will be assumed to be smooth over complex vector spaces. Representation pi v of G is said to be H distinguished or distinguished by H if the space on H pi C of is non-zero, which means that there is a non-zero H-invariant linear form from V on V. Now consider the two following problems, or the two following questions. First, how can we classify the H-distinguished irreducible representations of G? And second question, if you are given a distinguished representation of G, what is the dimension of this space of H-invariant linear form? I will start by giving an answer to the second question. So there is the following theorem due to Guo in the split case and to Broussus and Matringe in general. In general, with the only assumption that the characteristic of the field F is assumed to be non-zero. For any irreducible representation pi of G, so first, the dimension of the space of H-invariant linear form is at most 1. And if this dimension is equal to 1, then the representation pi is self-dual. Self-dual, or if you prefer, self-contragradient, so which means that the contragradient of pi is isomorphic to pi itself. Now let us consider the first question, how to characterize those irreducible representations of G that are distinguished by H. There is a conjecture which has been proposed by Prasad and Takloo-Bighash. About 10 years ago, in 2011, which says the following. So first, let pi be some irreducible representation of G.
Sorry, Vincent. Actually, I guess there's a little bit of a lighting problem. So basically what you wrote, that's in a shaded area. But outside from that, it's again good. From conjecture, okay. Prasad, Takloo, and then pi in irreducible of G, that is a shaded area of the blackboard. And I don't know if people can read that. But outside from that, it seems to be better lighting.
Okay. Okay. I will denote by JL pi its Jacques-Langlands transfer. To the split form GL2NF, and by phi its Langlands parameter from the Weideling group of F to GL2N C. The conjecture has two parts. The first part is the following one. It gives a necessary condition of distinction. Suppose the Jacques-Langlands transfer of pi is generic. If pi is H distinguished, then the two following conditions are fulfilled. First, the Langlands parameter phi takes values in the symplectic group SP2NC. And second, the root number, that is the value at 1/2 of the epsilon factor of the restriction of phi to the Weil group of K, is equal to -1 to the air. So this is the first part of the conjecture, and the second part is as follows. It gives, it tells you that this necessary condition is sufficient for the discrete series representation. So if pi is in the discrete series of G, or if you prefer, is essentially square integrable and satisfies A and B, then it is H distinguished. Let me make a couple of remarks about this conjecture. So the first remark is that Prasad and Takloo-Bighash give a more general condition for the space home H by mu to be non-zero for an arbitrary character mu of H, and not so mu is not necessarily the trivial character. And so this conjecture can be seen as a generalization of results by Tunnel and Saito, which correspond to the case where n is equal to 1. So what is known about this conjecture? So several people have contributed to proving this conjecture, but I will focus on very recent developments only. So from now on, I will assume that F has characteristic 0 for the remainder of the talk. So first, Hongshui proved the first part of the conjecture, C1, so the proof that the conditions given by Prasad and Takloo-Bighash are necessary for pi essentially square integrable. And later, Miyu Suzuki has extended C1 to any irreducible representation. So remember that in C1 there is an extra assumption. Prasad and Takloo-Bighash assume that the Jacques Langlands transfer of pi is generic, and actually it turns out that this extra assumption is not needed, as observed by Suzuki. And the Suzuki and Hongshui proved that C2, so the second part of the conjecture about the essentially square integrable representations, reduces to the case where P is cuspidal. So it remains to explain what happens in the cuspidal case. And so here is the result I would like to discuss in this talk. So assume F has characteristic 0, and assume also that the residue characteristic P is different from 2. Then, assuming this, C2 holds for cuspidal representations. So this gives altogether, this gives the full proof of the Prasad and Takloo-Bighash conjecture, assuming, of course, these two assumptions. Let me insist on the following fact. So why is it necessary to assume that the characteristic of F is 0? So the theorem requires F to have characteristic 0 because its proof relies on a weak form of Schur's result. So it does not entirely rely on this full result, but only on the following part, which I will note with a star. If pi is cuspidal and H distinguished, then its Langlands parameter has a symplectic type. So this, I will use it as a black box. And from there, I'm going to explain how one can prove C2 for cuspidal representations. Basically, the strategy is the following. Starting from this weak form of Schur's result, star, the strategy is first prove that any pi cuspidal H distinguished satisfies the Prasad and Takloo-Bighash conditions. And second, prove that this implication is an equivalence by a counting argument. So I would like to explain that in more details. In particular, a counting argument requires a finite set. So I will have to introduce finite sets, so which I will do now. So let gamma be an irreducible representation of PF, which is the wild high inertia subgroup of the veil group of F. So PF is the unique maximal Propy subgroup of the veil group. I choose an irreducible representation of PF, and I will assume that gamma is non-trivial, is not the trivial character, for simplicity in this talk. And let gamma denote the WF conjugacy class of small gamma, and assume that this conjugacy class contains the contragradient of gamma. The reason for this is that we are interested in self-dual representations only. because being self-dual is a necessary condition for being distinguished. Now, let me introduce the following sets. First, I will denote by A, G, gamma, the set of cuspidal self-dual representation pi of G such that the Langlands parameter phi contains gamma when restricted to the wide inertia subgroup. I will denote by ASP the subset of A made of cuspidal representation pi such that phi is symplectic. And by A PTB, as you can guess, the subset made of cuspidal representation in ASP such that the root number of the conjecture has the right value, -1 to the r. And at last, A disk is, of course, the set of cuspidal representation pi in A, which are H distinguished. All these sets are contained in A, and this one is finite because gamma has been fixed and the cuspidal representations are all self-dual. So now that I have introduced this finite set, the strategy is the following: prove that A dist is contained in APTB, and prove that they have the same cardinality. So now I would like to talk about steps, about how one can construct explicit models of cuspidal representations of GLN or of inner forms of GLN by compact induction. And this I will use to construct H distinguished cuspidal representations of G. So the first, any cuspidal representation pi of G has a model of the following form. So pi is isomorphic to the compact induction from J to G of lambda, where J is an open compact mode center subgroup of G, and lambda is a specific irreducible representation of J. So J and lambda here are explicitly constructed in a very specific way. They are not arbitrary at all. It goes back, their construction goes back the speed case to Bushnell and Kutzko. And it has been, the construction has been extended to inner forms of GLN by Paul Brussels, Martin Graditz, myself, and as well Sean Stevens. So a pair J lambda is called a type, or a simple type, more specifically, and it has the following properties. The first property is that J has a unique maximal, normal, pro-P subgroup, which I will denote J1. Second, lambda decomposes as a tensor product, lambda W tensor lambda T. So W is for the wild part and T is for the tame part. Such a decomposition is not unique. There is no canonical choice in general, but it exists. And lambda W has the property that when restricted to J1, it remains irreducible, and lambda T, when restricted to J1, it is trivial. Third property, the group J mod J1 can be explicitly described. It is a semi-direct product of a finite general linear group GLML, semi-direct product with some Galois group, where M is some divisor of 2n, and K and L are both finite extensions of the residue field Kf of F. And the last property I will need is the following one. If you restrict, so by construction, lambda T is trivial on J1, so you may think of it as a representation of J mod J1, and you can restrict it to the finite general linear group, GLML, and it is required in the construction that lambda T restricts to a cuspidal representation of this subgroup GLML. So this is what happens for any cuspidal representation of GL2N, or more generally for any cuspidal representation of an inner form. But what if the cuspidal representation is self-dual? What can we do? What can we improve if we assume that the representation is self-dual? So what if I is self-dual? More precisely, we would like to choose the wild part lambda W as follows. First, we would like that lambda W is tau self-dual. So remember that tau is the inner involution which can be used to define the subgroup H. And so tau self-dual, what does it mean? it means that lambda W composed with tau is isomorphic to its contragradient. And we would also like to choose lambda W so that it is J intersect H distinguished. And if such a choice is possible, then the following map So I will denote by capital pi of rho the compact induction from J to G of lambda W tensor rho. So I will explain what rho is in a minute. Produces H distinguished cuspidal representations of G. So for what kind of rho? For any representation rho, the irreducible representation rho of J mod J1, which is cuspidal. And so cuspidal, of course, means that when restricted to the finite GLML, it is cuspidal. Cuspidal and J intersect H distinguished. So this machinery produces H distinguished cuspidal representations of G. So we are reduced to consider cuspidal distinguished representation of a finite general linear group. But for our counting argument, we need to construct not only cuspidal distinguished representation of G, but representations which are in A with a fixed gamma on the Galois side. And it turns out that it works. So it comes from the type theoretic interpretation by Bushnell and Enyart of the W conjugacy class gamma. So it amounts to saying that fixing lambda W in this construction is equivalent to fixing the WF conjugacy class gamma, which I introduced earlier. And a consequence of that is that for all rho, the cuspidal representation pi of rho belongs to the finite set A, where gamma has been fixed. So now it remains to count representations.
So, sorry, a quick question, Vincent. What is gamma? I forgot what capital gamma.
So we consider a cuspidal representation pi such that if you look at the Langlands parameter phi and if you restrict it to the wild inertia subgroup, you want it to contain gamma, small gamma, and gamma is the WF conjugacy class of this small gamma.
Thank you.
Okay, now we have the following counting statement. So first, any representation in A is of the form pi of rho for some rho, for some cuspidal representation rho of J mod J1, not necessarily distinguished. Second, for any rho, there is a quadratic character omega of J mod J1 such that pi of rho is distinguished if and only if pi of rho omega is not distinguished. So it allows you to prove that half of A is distinguished and half of A is not distinguished. And so the map pi produces 1/2 of the cardinality of A distinguished representations. So I have cheated a little bit. Actually, at this stage, you cannot deduce that the representations which are not in the image, you cannot deduce that they are exactly half of the cardinality of H distinguished representation, but there are at least this number of representations which are distinguished. And I will come back later on that point. So now let's consider the stabilizer of gamma in WF. So it is a subgroup of WF of finite index. So it has the form WT, where T over F is finite, and it is thinly ramified because gamma is a representation of the wide inertia subgroup. And now do the same with gamma plus its contragradient. So by assumption, since we consider only self-dual representations, we have assumed that gamma check is conjugate to gamma under WF. So this stabilizer is slightly bigger than the previous one, and more precisely, the extension T over T0 is quadratic. So this, of course, works because I have assumed that gamma is not the trivial character. If gamma is a trivial character, it is a particular case, special case which has to be treated in a slightly different way. And also, I will need the following notation. Denote, so call degree of gamma the dimension of small gamma times the degree of the extension T over F. And there is the following statement. For any representation pi in A, so cuspidal and self-dual in A, the following assumptions are equivalent. First, First condition, pi contains a type lambda, which can be decomposed into lambda w tensor lambda t with a lambda w as we would like, which means tau self-dual and j intersect h distinguished. Second equivalent condition, the root number is the right one up to small detail, the determinant of phi at -1, but it is not important because for representations of symplectic type, it will be automatically trivial. And third condition, which is equivalent to previous one, so which is a numerical condition, 2n over the degree of gamma, which is an integer, and the integer r have the same parity, and alpha is, so what is alpha? Alpha is the square of delta. Alpha is the element in F cross which characterizes the quadratic extension K over F, and alpha is a norm with respect to T mod T0 if and only if R is even. So first you can see that this condition is satisfied, this type theoretical condition is satisfied if and only if the epsilon factor has the right value. It is already a striking fact. And now, what is the relation with distinction? This is given by the following theorem. If phi is distinguished, then the condition 3 above is satisfied. Which means that in order to prove that distinguished implies that the Prasad Takloo-Bighash conditions are satisfied, we do not, we pass, we use an intermediate step. We verify this numerical condition. And now, we are ready to finish the proof of the main statement, the corollary. So first, this proves that the set of distinguished cuspidal representations satisfies the Prasad and Takloo-Bighash condition, and we also know that there exists a cuspidal, a distinguished representation in A, if and only if APTB is not empty. So this one is contained in that one, and either they are both empty or they are both non-empty. And second part of the corollary, if there exists a distinguished representation in A, then what does it mean? According to theorem 3, condition 3 is satisfied, and according to theorem 2, is condition 3 is satisfied, then there exists a lambda W as we would like, which allows us to produce a certain number of distinguished representation. So if A dist is not empty, then automatically, if it is not empty, it must have cardinality at least half of the cardinality of A. And now, what do we have? We have this containment. Suppose that we are in the case where both are not empty. We have this containment. This set has cardinality at least half of the cardinality of A. So it remains to prove that that set has cardinality at most half of the cardinality of A. And in the case where it is not empty, there is something I did not say. It is that APTB, it is the same as ASP, because if the root number takes the right value for one representation, it will take the right value for all the representations in A. And because of the dichotomy between symplectic type and orthogonal type, we can prove that this one has cardinality half of the cardinality of A, and we are done. Thank you.
Do we have questions for the speaker?
I just had a naive question. With the case that gamma equals 1, would that then correspond to the tame case, or only the tame representation?
Tame in what sense?
Oh, whatever sense would make the question make sense.
Okay, so when gamma is the trivial character, it corresponds to the level 0 case. It corresponds to level 0 cuspidal representations. And in the level 0 case, T and T0 are the same. So T mod T0 is not a quadratic extension. And so you have to formulate things in a slightly different way, but the general counting argument has the same structure.
Are there any other questions? Well, if not, we can thank the speaker again. Stop recording.